This stuff is supposed to be about 40 minutes, right?
So today's presentation is by Daniel Ramirez, who will try to practice his second year seminar once again. So we can check other improvements or other opposite compared to previous attempts. If you wave hand, it will be a trace.
Oh no. Dang, I missed it. So,
Go ahead.
so mainly, I'll be talking about a certain type of material that has a chemical structure, which is referred to as ABX3. This type of material that I'm talking about is called perovskites. There's a list of pros and cons to them. They have a tunable band gap, really stable material. They have high quantum yields. Certain perovskites exhibit a material where they have long charge carrier lifetimes, and they're excellent charge removals. There is a couple of negatives to them. They have poor stability and moisture, so they degrade when water is found. They don't do so well when the temperature's hot, and they have a structure that varies depending on the temperature that they're in. But most of the time, we're gonna be talking about it in room temperature, where the structure is the one shown right there, which is just a tetragonal shape. So the chemicals ABX3, A is usually referring to an organic cation such as methylammonium or formandidium, and there's also cases where they use an inorganic cation such as cesium. So B is usually a divalent metal such as lead 2 or tin 2. X is just a halide, just your average halide. So there's a couple of things to go along with perovskites that we're trying to improve. Is the effect of light. We're trying to, in the case of LED application, we want a release of light. So some of these structures, the light is sometimes removed, which is just negative for LED application. I'll be mentioning that a little bit later. So there's also a thing called trap states. We want to try to minimize those as much as possible. And also another thing is we try to increase or try to keep the photoluminescence quantum yield at an all-time high. We don't want any type of quenching or removal of it. And reducing non-radiated recombination is also another key aspect to this, because during the process of non-radiated recombination, some energy is lost due to cooling and thermalization. So lost energy is a negative aspect in charge transfer mechanisms. So reason why perovskites might be a suitable contender to this is we want to try to increase technology that relates to solar energy, because it's an all-time low. It's really can be seen as a material that can probably benefit and increase the percentage of this. So normally there's types of energies that we're taking into account right now. It's tidal energy, geothermal energy, hydro energy, or just water, biomass energy, wind energy, and well, the end game goal is trying to harvest the sun. seeing as how the sun is a great potential that seemingly we're not really taking advantage of it. As you see, we're only using 1%, or less than 1% of our energy is coming from solar products. Well, the long-term goal, according to the study found in 2015, the world energy consumption is at 18.5 terawatts. Most of these energies combined can already support that, but more long down the road, we will probably be running down into an energy crisis. Well, right now we're being sustained with more renewable energy, but renewable energy is hopefully going to be the end game goal. So there is a potential market for this. According to the rest of the world, there is investments in this. More and more people are investing into this. It is and probably will be a valuable source of energy one day. Currently right now, totally, it's been increasing each and every year since the introduction, or well, since most people have been trying to provide it. So hopefully it will get up to a point where 2018 we're only providing gigawatts. We're not even providing terawatts. Yes.
Just wondering, is it interruption or should we continuous talk? Should we ask later? Can you ask question in the middle or?
I guess, yeah, the rules don't permit anyone to interrupt.
Oh, okay.
Even
Now
when
you
you
practice
present.
talk, that's one was wondering.
You have a question?
Yeah, I'm just wondering about your titles and what are you talking about so far. I'm not. What is this, emitting application, light emitting applications, and you're talking about all solar cell and everything.
Yeah, I see what you mean now. I'm a little confused right there. Yeah.
Yeah, just comment.
Well,
here. It's
No,
not-
that's a great comment. Yeah.
You need to have a slide explaining kind of main goals,
Okay.
because you jump to some
Right, yeah.
specific right away, and your title not really helping to not really tells anything
Yes.
when you go to the next slide.
Okay.
Right?
Yeah.
So can you start with the goals first?
Goals. Okay. Yeah.
And maybe outline. Like,
Return back from your title, and you can, again, you don't need to have additional slide. Then you can just say it to people, right?
Mm-hmm.
Hoping that everyone will listening to you.
Hopefully, listen.
So of course it's better if you have a slide.
Okay.
So, but suppose you don't, but you definitely need to explain people what are the goals of this presentation and kind of, so people know what to expect here.
Mm-hmm. So pretty much just start from here and talk
Yeah,
about
it just exploded for you. now.
Okay. So the whole point to LEDs are we're trying to maximize radiative recombination, because during this process, radiative recombination, there is a photon or a photon that is released as light. So with that light, we can redirect it, and with that, we could probably tune it into whatever color we want. So depending on what type of visible spectral light you want, that'll be a great application for that.
What are you going to tune and how are you going to tune?
So ABX 3 molecules are perovskites.
What is ABX3 molecules?
It's just
Oh,
the
this is
chemical structure.
perovskite.
Yes.
Okay,
I could
So
probably
you
put
actually-
perovskite instead.
you talk about defects in perovskites,
Yeah.
and your main kind of point here that defects is good for emitting light application or bad. You want to eliminate it, or you want to use this as a tool for controlling the emitting applications.
As a tool.
Okay, so then again, you kind of have a provocative title, which is really good because it can catch the attention right away. So you say defects in perovskite, you definitely need to identify the material, right?
Okay.
So in perovskite for light emitting applications, and you can really start saying, well, typically defects is something bad. And usually defects means they not emit, they kind of have the trap states, blah, blah. But for perovskites, defects doing some good things.
Mm-hmm.
And you will be really discussing what's really special about perovskite, why defects in perovskite helps to improve the emission.
Okay.
And then this would be your goal. Maybe, I don't know exactly what are your goals. You still didn't explain to me what your goals
Okay.
for this one. But you
Yes.
got it, right? You can really start with a kind of provocative statement, because usually defects not doing good thing for emission. Defects usually leads to quenching of emission.
Yeah.
But you're trying to say that in contrast to a typical approach to defects in bulk materials or even in other nanostructures such as quantum dots, for example, right? Here for perovskite, defects actually make a good thing for increasing emission and can be used as a tool to tune these emission properties, which of course is promising. And why and how this works, this is what I will tell you during this presentation.
Okay. Yeah. Thank you for that. Appreciate it. So this is some of the advances that have been done with cells trying to convert.
I think you skipped a slide.
Oh, I was on this one.
Oh, you were on this one.
Yeah.
Okay, never mind then.
So this is from the National Research Energy Laboratory. These are pretty much all types of energy harvesting cells that have been produced since the beginning of the induction back in 1975-ish. But for the purpose of this talk, I'll be mentioning what's in that red line over there that's highlighted, primarily perovskite structures. So over the past couple of years, it was just recently, about 2011, where they started this type of research, and you've seen the exponential growth over the times where it keeps increasing over time. It's still a fairly new material that's being heavily looked at nowadays, but hopefully has the potential of reaching up to efficiencies up to 30%, and also could be a primary contender to silicon cells, which are also low cost. Well, so there's a couple of applications that perovskites are seen usually for. Photovoltaics is one of them, where we want a recombination of the charge when we apply a current to the cell. The electrons will flow from the what is usually known as the conduction, the valence band into the conduction band, and a photovoltaic cell.
So what do you call conduction and valence band? Because again, you're not giving a talk to physicists. Some people might be really not using this terminology and might be lost.
So it's usually, chemists usually refer to as the HOMO and LUMO.
Which again, not necessarily that everyone understands this language.
I thought it was like Gen Chem. I thought everybody would understand this language.
Really?
I thought it was in Gen Chem, wasn't it?
You may remind it.
But maybe instead of using abbreviation, you can really name it, right?
Yes.
And then use abbreviation.
Okay. Yeah. So it's usually referred to as the highest occupied molecular orbital, which is commonly referred to as HOMO in literature. And also, the electrons are usually found to be in here. When you excite a semiconductor, the electrons will flow from the highest occupied molecular orbital up to the lowest unoccupied molecular orbital.
Is it flow or just
flow?
I guess.
Flow. Huh?
Is it flow or excited to that?
I guess you can say
Transfer.
excite, transfer.
Or transfer, yeah.
Move.
I guess there's a lot of words for it. I always have a hard time using the right word for this. But
Oh, flow is
Flow is
it's cool.
flow is cool. So yeah, in the case of photovoltaics, we want this to be a continuing process to keep harvesting said energy. And then, well, for the purpose of my talk today, light emitting diodes, we will be following the same process of, usually the N-type is,
Before you go there, I still didn't understand. You spent about 5 minutes at least, or maybe even 10 minutes for your, how many, 3-5 slides before, right?
Okay.
And can you again just tell by your own words why you were showing me all the slides on the photovoltaic applications and then move into the light emitting diodes, if your title is really about emitting applications, not photovoltaic applications? And again, it's completely okay to do this, but you need connections. You need to say it by words so people will be with you. Not really looking on a slide, just explain it to us.
So the purpose for this?
And you can really just, before going to, you can say, so why did I tell you all the story about photovoltaics while I'm really going to talk about light emitting diodes? Guess why? And then you answer it probably, because people probably will be not have no ideas why you're doing it. But you should know, right?
Yeah.
So why?
Why? Well, because these materials have the potential for both applications. We really can't forget one or the other because some findings may find...
Okay, then I just suggest, and again, you can do it in your own way, but you need this kind of things.
Okay.
Really, when you come home, think about how you can... So I'm just taking your idea, and instead of saying it in a slide number, whatever, 10, or whatever your slide numbers there,
Yeah, sorry.
so when you say your, again, either with a slide or just by words about your goals, right? And then coming to the next slide where you say perovskites, right? You really can say there, the same words as you say there. So although my focus for this talk will be on the light emitting diodes as emitting applications, you probably know that like nowadays the word perovskite is used usually for the completely, not completely different, for the photovoltaic applications. They have a great promise, and then you go and talking about this material in the terms of the most common, most exciting, most well-known application. And then when you go to that slide, then you can again make a pause and say, well, so you still can say, this is good for photovoltaics, but why are you interested in perovskites for the light emitting diodes? Well, first of all, the processes which you show are really just reverse comparing to the photovoltaics.
Yeah.
And this is actually the purpose of these two slides, right? And this gives, if you really do it by your own words, right, and really talking with people sitting in front of you, I think they really remember it and they will really like this approach. And no one will be, I mean, they might be kind of confused why you start talking about photovoltaics, but because you already put your intrigue there. They really appreciate it, and maybe they really remember your talk much better than anyone who would really be very, how to say, academic and very official in a way of just, because I'm talking about light emitting diodes, I will talk only about light emitting diodes.
Yeah.
Right? So nothing wrong with this approach, but you need to connect everything. And again, you can make it, you don't need slides for this. You can just, don't forget to talk with your auditorium and really put these connections.
Okay.
So, and I would suggest, really, don't go with your slide number 2 or 3 for perovskite, but really kind of say, you can make even jokes, you can post questions to auditorium.
Okay.
Make sense?
Yeah.
So suppose you're already connected.
Suppose already connected. Yeah. So, in the purpose of LEDs.
Oh, can I interrupt?
It looks like you didn't make a connection.
Just a suggestion. Again, you may find some better ways. It's just an option.
Yeah.
So first you tell perovskites are popular, they have some features, people cite them like crazy. And then if you build, fabricate a diode out of perovskite, then you can ask audience, do you remember what is diode? Then it can work in 2 ways. If you let current flow through it, it may shine light. If you shine a light on it, it may give you a current. This serves as a source for 2 industrial applications: collecting light or emitting light.
Yeah, that's sort of the take I was trying to go for. Because I mean, sometimes you might find out you're trying to study LEDs, but the process might, or the results might tell you that it serves as best for photovoltaics and LEDs. But I just want people to know that it can just be used for both, not just one.
So it's 2 sides of the same process. It's like title of the next talk, Janus. You look at it's Janus of perovskite diode.
Yeah.
I have a question, sir. Maybe.
And we have an expert here. We still don't know how to pronounce this name.
It's Janus.
Janus, not
I'm
Janus.
not right. No.
Janus. This is really name of a god, right?
Yes, and the classical pronunciation is
Yes.
Janus. But if
Classical.
classical
You're not
Latin,
talking Greek or Latin right now, right?
in the classical Latin pronunciation. If
Oh,
you
in Latin,
if you
okay.
want
But what
like
about English?
if you want an English pronunciation, it's Janus.
Ah, okay. But if it's Latin, then it's Janus.
Janus.
Janus most
Janus.
How would you feel
better for me.
Janus.
Janus.
So
Yes.
maybe it's irrelevant question, but I'm just wondering, you're Fermi leveling these images. Why is banded to be? Isn't it Fermi level need to be aligned here? I don't know. I'm just asking. I'm just wondering. You took from literature. I know that this is the right feature, but I don't know why.
So I'll tell you. I won't tell seminar. This is a Wikipedia image.
Okay.
Yes.
Okay.
So yeah. That's probably why they include sources, because it didn't come from lecture. I mean, from literature.
They do have like sources like on
Yeah,
the image
you can
page.
source
Yeah,
like
yeah.
Wikipedia.
I know what you mean. Yeah.
Source like Wikimedia.
Okay. So, for the most part, the beginning of the mechanism is almost similar to the photovoltaics, where we excite where the material gets excited and the electrons flow from the valence band up to the conduction band. But the difference in between the both and an LED is when it relaxes. If you remember from earlier where I told you, the conduction band is the LUMO, so the lowest unoccupied molecular orbital. The electrons don't really hang out there. They like to relax back down to where they originally started, in the highest occupied molecular orbital. So in this process of it relaxing down, there is an energy that's given off. Usually this little term light is, we usually refer to as a photon, but it's the same thing as a light. It's given off, whereas in photovoltaic cells, we want to harvest it, and LEDs, we want that emission of light. So if you're more of a physicist, this is sort of the that current diagram, and this right here is just the emission of light. So there's two types of recombination that occur, where this one is the one I just recently explained to you about how the electron will flow or relax from the lowest unoccupied molecular orbital to the highest occupied molecular orbital, and that's what it's called the radiative recombination. Also, where the light is given off, and the term is called a photon. And then here is the other word that I mentioned, was the non-radiative recombination. So in this process, there are multiple lowest unoccupied molecular orbitals. When I go back, this right here, the conduction band, is usually the lowest unoccupied frontier orbital. So that just says it's the lowest excited state in energy. There are multiple energy levels that are higher than that. So when it tries to relax down to the energy state, there is a form of energy that's lost, and that is a negative. The energy is lost as heat, so we want to try to minimize that, because keeping energy to a maximum is key to basically this mechanism. So yeah, it says it right there. We also lose efficiency, which is a bad thing. We want to try to keep efficiency as max as possible as a well-oiled machine. So what makes perovskites unique in their own character is their high, so they accept the band gap tunability. So what we mean is we're allowed to try to choose what type of energy current it is between both of them. So being able to excite from the HOMO to the LUMO is a huge goal and challenge. So usually we need to give it a certain amount of energy to be able to go that. The higher the band gap, the less likely that material is ideal. So depending on what type of halide or X you use, you get a different type of light emission. So high wavelength is lower energy, so the band gap will be lower. Well, if we approach the more new UV range, the energy is higher, so it costs us more to excite from the HOMO to the LUMO. And here, when I mentioned earlier quantum yields, these perovskite structures in the colloidal nanocrystal structures, they're found to have a quantum yield of 50 to 90%. So what quantum yield is the number of emitted photons over the number of absorbed photons at the excited wavelength. So it's just more of a ratio. The higher, the better, obviously. We want to try to get as much emission as we get absorption. And we can also relate the emission of the light into a excitation. So usually a lower rate on these is much more ideal. So the higher costing bandgap halides are more ideal than the lower bandgap cost of the iodide compared to the chlorine halides. Yeah.
Ideal means in what sense or what perspective I don't get it.
Ideal. So
you said is blue is better than red one?
blue is better than red one. Yes.
But why?
Because why? Because the rate of relaxation is much faster in that one. So.
But when we need the red light, we cannot use the blue light there. We need the red light.
I guess in that aspect, we will change it. Just depends. I guess the application you're looking for or the emission of light. But normally, if it's lower band gap, such as the red light, it's gonna cost us less in energy to start the process. Well, if we go down to the blue light, it'll cost significantly much more energy to excite it, and sometimes higher band gaps are a lot more difficult to deal with. Unless you got a better explanation for that.
Aren't you exciting it via the electric energy? So you're not using a light to excite in an LED, you're using typically
Current.
Yes.
Yes.
So you're exciting it using voltage, right?
Yes.
Which means that low energy and medium energy could cost the same amount because you have your anode and cathode that are at a specific voltage and then they go down,
Okay.
right?
Huh.
So it might not be that the red costs more energy than the blue. You lose a lot more in the red than the blue, right?
You lose a lot more in the red than the blue.
Yeah, because if your anode and cathode are at a specific voltage,
Okay.
and then you cascade to the ferrimolecular orbital before combining to make a photon, red, you have to go further down compared to blue.
By those are different materials, they have a different band gap. Why you think that they're exciting with the same energy?
In this experiment,
I
they're
don't know
probably
this
not.
I'm saying, okay, yeah.
But I'm saying in LEDs, it's
Mhm.
different than in colloidal solution excited by
Okay.
light.
I don't know what they explain. Maybe they have some relation with this figure.
Well, yes. So, the time scale between the relaxation rates of these onto this happens to be in the nanosecond range, where the max, the iodide solution is found to relax in 29 seconds compared to the blue version that's found to be 1 nanosecond relaxation. So chlorine isn't included because they had difficulties with it, but it probably was too fast for the machines to discover it or to detect it. But yeah, man, I'll look into this a little bit more. I didn't think about it too much. Thank you.
So I have a one-side question. So
Yeah,
is
go
that pure perovskite or any defected perovskite?
Excuse me?
Those are pure perovskite, right?
Yeah, these are perovskites.
I mean,
Are they-
pure perovskite? I mean, not pure, I mean,
PU.
defect-free perovskite or defected perovskite?
I believe they're just defect-free. They're just
Yeah.
colloidal nanocrystals. It's just one of the first papers that came out, and all the quantum yields that came out.
Because the alternate pool is defect, so it's on this one, right?
No, yeah, I'll talk about defects stuff more later on. I started finding a bunch of papers on that stuff, so I found it interesting. Yes.
So when you talk about quantum yield, is quantum yield a number or is quantum yield a function?
Quantum yield.
It's a very open-ended question.
I believe it is a number. You can correct me though if I'm wrong.
Does it change with wavelength?
Yes, because it depends on the excitation of the wavelength. So it is a function. Oh, thank you. Great question.
It is also a function of charge carrier density. So if you already have like 2 electrons in a nanocrystal at one time, if you add a third, that's going to reduce your quantum yield because of higher order effects. Yeah.
Isn't like adding a third also then you have to take into account like OJ non-recombination?
Exactly, that's what makes them less efficient.
Okay, yeah. I mean, I read about it, but I haven't been introduced to it that well. I just barely know the basics of that.
So you might get a question on there. Someone, professor, will probably ask you. It's like something about charge density, if that plays any role for. Because it will for LEDs, because you have to pump a lot of electrons into them,
Okay. Good.
and then they kind of limit their efficiencies too. So I got a question for you that you might get asked. So why does changing the halide change the color or change the band gap?
Why does changing the the halide change the band gap or the light emission?
Which is changing the band gap too, so that's where
Oh yeah.
it comes from. So we'll get in there.
I think it probably has to do to the size of the halides themselves, where iodine is rather huge compared to chlorine, and that's probably part of the band gap tunability. It's being able to select the specific halide. Hopefully, that's suffice enough. Even though it's probably a general answer.
I think I kind of tangentially, so like size of your ion.
Yeah.
So it's like, that's the same thing as like ionic radius, right?
Ionic radius.
So-
Yeah.
I think the easy way to think about it is if you look at a periodic table, like if you're trying to explain it to chemists, if you look at where lead is compared to iodide. So
Are
if
they
you,
on the same row?
they're not in the same row, but if you just compare like the halide,
Yeah.
their rows, so your iodine and your lead are going to be closer in energy. So they're going to be, their energy difference is this. They could go up to bromine. It's like that's going to be a bigger energy difference. And then chlorine's going to have the biggest energy difference.
Okay. So when you mean ionic radius, you mean kind of like the ionization, sort of.
Right.
Yeah.
That's the way I think about it anyway.
Okay.
If I had to explain it to a
To
bunch of-
chemists. Yes. Thank you. Thank you for that. Any more? Yes.
The question, suggestion, what to put before the slide and after the slide. Not necessarily as a new slide, just verbally.
Okay.
So before the slide, what are industrial requirements for photovoltaics and for light emission?
Okay.
So here you are showing the whole range probably. It's self-evident, but you didn't declare, like if you want emit light for humans, for lightning or for the displays, it should cover the whole spectrum. So you're addressing this industrial requirement. And to follow up this slide, you show horizontal arrows for each group of like cesium, lead, iodine, then cesium, lead, bromide, and there is an arrow showing the range. So to address the difference of the wavelengths within the same chemical composition, you may remind to our audience what is quantum confinement and what is the equation for the ground state of the particle in the box.
Yeah.
Right? Which we do not doubt that you know from the top of your head.
Yeah, audience would love long equations.
It's very brief equation.
No, yeah, I'm planning on adding a lot of equations too.
But
They'll enjoy it.
sure, explaining this tuning of the frequency with size, what you already partially touched, would be very relevant. Although it is not major goal of your talk, it will be like good illustration.
Yes.
Okay.
So here's a DFT study that was done in Italy. So for most of you, if you've never heard of DFT, it just stands for density functional theory. Density functional theory. The whole point to this is to try to solve the particle in a box equation using trying to solve time-dependent Schrödinger equation for a many electron system. Well, that's a huge case. We use BAS for that case. Well, and mine personally, but so they used a method that's called PBE. It is an upgrade, a step up from the most basic method that most people usually know as Hartree-Fock. But besides the point of that, so there was a DFT study done on the thermodynamics field of stability. So the methylammonium lead iodide was found out to be stable. So they took the potential of lead, the chemical potential of lead, and the chemical potential of iodide, and this linear line is stating the stability between both of them. So it is found to be a very stable calculation. And here in the other side, they calculated the band gaps using a number of different methods. So HSC is just it's a much higher level of method or theory than PBE, because how a lot of these methods work is they use a different different percentages of Hartree-Fock. So the reason for that is if you try to use as little as possible as lowest percentage of Hartree-Fock, the computational cost is vastly increased for more accurate results, but at the same time much longer results to get back in time. Which they found out that these methods, they were in great agreement within experimental results. So the higher computational cost wasn't, I guess, wasn't worth the cost at the time. So they found out that the band gap using this method was 1.56 electron volts, which is great agreement in with experimental. So there's what this star is referring to. They took the PBE, and this one they included spin orbit coupling. So they took into consideration the spin of the electrons instead of not doing it. So it's much higher computational cost. So they found out the band gap for this one was 0.55 electron volts. While we also see some encroachment of the valence band into, we see it more increased more. So that is in agreement with experimental. Well, they also look into this method and they increased the radius of the molecule. Well, they found out it actually had the adverse effect. While the band gap did increase by double, we saw a opposite effect where the valence band kind of suckered up and got further apart. Yes.
Okay. I'm just wondering one thing, it's not a specific question.
Okay.
So, what do you learn from this slide and how is it related with previous slide and next slide?
I'm trying to go based. I included this one based to the fact that a lot of people don't really see DFT as a viable option. They think that well, that or not a lot of people are exposed to computational chemistry. So I just want to let the public know that there's a lot of results that show great with experimental results. So just because it's not done on a
Where's the
desk,
experiment?
Where's the experimental? So in the paper they just stated it, and I could probably look into those references.
So I guess make it easy. Then what do you learn from this slide? Just give us one sentence.
Computational chemistry helps aid experimentalists. Or
That's a very general word. It's true.
Let's read the title of your slide.
To illustrate the idea that computational chemistry helps experimentalists, you just need a cartoon, a computer, a person, lab code, and then arrow between and word help. So you do not need any results.
okay.
And don't we already know that it's stable because they see stable quantum dots in experiment?
Okay. Yeah, I guess so. I guess I should probably not include this slide then. Thank you. Really isn't anything, is it? Thank you.
Other questions?
Oh yeah, go ahead. I encourage all questions.
Well, I'm just sort of confused on the panel A. I don't really understand what's happening. So as I go from like the top right corner, and if I make a line strictly 45 degrees
Okay.
to the bottom left, what's happening? Just a proportion of methyl ammonium and lead is changing, or
Well, so that's just the chemical potential of lead. That's I guess the horizontal axis is for, and then the vertical axis is the chemical potential of iodide. So usually in this shape right here, you really can't see it, but in the center of this little tetragonal thing is where the lead is in. It's in a organic cage, and the one that's holding the cage are the iodides surrounding it. So it is found that they're happy to be with each other, and that's just the way it is. I could probably look into this a little bit more, but yeah.
so what's happening in the light blue and the dark blue regions? I'm just confused about the notation.
No, yeah. So the blue notation is the methylammonium iodide. While the light blue is just the lead iodide, or yeah. And I guess it's just a combination of both of them. Where this line in the middle is just the overall structure, the methylammonium lead iodide, the 3. This one has a 2.
Is it showing where each compound is stable, and if it's not in the stable conformation, it will convert to the most stable conformation?
Like a Fourier diagram?
Well, it's probably just trying to say like it's in
Like
equilibrium.
Gauss diagrams, something like that. Yeah.
Phase diagram.
Huh?
Just like a general phase.
Yeah, so like, if the chemical composition is not correct, it won't be a perovskite.
or it'll be, you get lead iodide, you know, or you just get chemical reactions. So you either get lead iodide formation or methyl ammonium iodide.
Actually, thank you for pointing that out. I didn't even notice they had the words in there. Alright, that was kind of hard. The light blue is hard to see, but yeah, thank you. So, a couple of defects. They calculated the defect formation energies from a couple things. So they found out that exposing a perovskite structure to a iodide gas, seemingly it increased quenching. So it actually improved photoluminescence quenching just by
So you said it increased photoluminescence by increasing the quenching.
well, no, quenching means it's killing it, so it's the adverse effect that we want. Right?
So it's decreasing the
Yeah, I'm sorry, I got my words mixed up. English is hard sometimes. Thank you for that clearing up. So it actually kills the photoluminescence.
No, I'm just gonna miss the one.
So it kills photoluminescence, and how it's doing this is when we add a iodide gas exposure to a perovskite structure, the iodides seem to bond inside. The increases the interstiticity. I gotta learn how to say that word, but basically they bond at the intersections of inside the cage. So when it is subject to high concentration of iodide, the structure goes from here, where this is the optimized structure, and it breaks down to this, where the intersection right here, they break apart, and it's not a tetragonal shape no more. It broke into seemingly not a tetragonal, it's the opposite. The effect that it had right here is it increased the vacancy of lead. It decreased the concentration of iodide, but increase the opposite effect. Obviously, if it's gonna decrease the concentration of iodide, the concentration of lead is gonna increase, or the vacancies of iodide are gonna increase, and the concentration of lead will increase due to this little snapshot that they took, where you see the iodides are not bonding to each other anymore. So that is how we get the increase in or decrease in iodide concentration and the increase in vacancies due to this effect.
What is DFE?
Defect formation energy. There was a equation. So what they took is they took the energy of the bulk, they got the energy of the charge, subtracted it to each other, or they added it to each other, then they took a subtraction of I forgot the rest of it, but it was like a four-parter. But yeah, there was an equation to what they solved for this.
I would suggest prepare as a slide if you don't remember all the details. And
Okay.
again, you don't need to show it right away, but if there is a question, you can,
Mhm.
with the citation exactly where these formulas are taken from, whatever, I guess this paper or
Yeah.
whatever.
Okay.
So then, if someone asks, at least you just can
Point
clearly
to-
explain how it
Yes.
was calculated.
Yeah.
Because it's really not a very trivial question, by the way, and what exactly they define by the surface energy and so on.
Yes, Ben.
So, just a question and a comment. I'll do my comment first. The little figures are a bit too hard to see,
Too
Okay.
little.
and so blowing those up at least like temporarily, like having a thing that slides up. And
Yeah.
that would be
Okay.
nice. So then my question is the thing on the left with the I'm assuming that's inorganic. Yeah, what does that mean?
The I. It's just
Yeah.
Plus
no-
0, plus minus, this is what you...
Yes.
I don't know what you mean.
Like that whole like left thing with the arrows.
Oh, this
What
stuff.
does that mean?
What does that mean?
I guess this is your charges, right?
Yeah.
Where? How are
The
they
charges?
different?
So apparently,
I guess it's reducing oxidizing, something like that.
yes, I guess it sort of goes back into right here where they tried to mention it a little bit. So obviously, in the valence band, we will have a negative charge because that's where our electrons are coming from. So where this is coming from then is just the number of iodides, because they usually refer to this as like a number of iodides that kind of combine into each other. So like right there, you see right here, I2 is equal to I positive charge is equal plus I negative charge. So that's sort of where they're coming from. And then right there as well is yeah, actually I don't really know, but yeah, I mean I looked at it. I guess I should have understood it a little bit more. Thank you. Sorry for that, but thank you though for that.
What is PLQ and PLE?
PLQ is photoluminescence quenching. PLE is photoluminescence efficiency. I could probably add a little text box to the side.
It's not enhancement?
Yeah, for enhancement.
It would seem intuitive if you have quenching,
Okay. Enhancement.
enhancing.
Oh, I guess I probably overlooked that too. Thank you.
So although I didn't follow you, I mean I didn't heard your whole slide. I'm just wondering, so it's changing only bulk, but surface is not changing. So is that the things you are talking about?
So
Seems like daily for bulk is change. I mean huge difference, but daily for surface is the same, almost
well,
same.
I guess it might be referring to the optimized structure. That's why it's probably delta E is just a change of energy. So
Oh.
it might just be in reference to the optimized structure. So I probably have to look into that too. But that's just my assumption. That's probably the only reason why you'd add a delta E too. You're comparing it to the optimized. Right here, they're just assuming over adding a concentration of iodide will do that. But any more questions on the quenching? If I can move on to the enhancing. So photoluminescence is enhanced. They found out that adding a low pressure of oxygen actually enhances the photoluminescence due to the effect where the oxygen would combine with the iodide and then form iodate, which in process makes the valence band lower in energy. So due to this fact, the enhancement, for the bulk surface is increased a little bit, and for on the surface as well. So this is due to the fact that if we see right here, when adding the oxygens, they bind with the leads and the iodides. Same thing with the to the divalent metal, and it's probably due to this more rigid structure, the fact that the photoluminescence is enhanced a little bit better.
So I have a question about panel F. You're saying that the iodate formation decreases the state. How does decreasing a state increase or change the quantum efficiency of the system? And how would making it more rigid also improve the PL?
Probably due to the physical properties of the more rigid structure. Normally we don't really see oxygen on a perovskite, but right here we see a successful binding to the metal and the iodide. But as you can tell from there, the iodine forms iodate. So it's probably due to, no, like you said, decreasing the energy of the valence band does not increase photoluminescence.
So then, if we look at the blue major box and the red major box,
Okay.
are they studying iodide or different halide for your perovskite?
For this one, they're studying the same.
No, but like if you take,
Yeah.
is it cesium or
Oh,
whatever?
It's methyl ammonium lead iodide. It's from that structure right there.
Oh, it's this structure.
Yeah, it's all from the same paper.
So then why are some of them red and some yellow?
Some yellow. So
Red is oxygen.
Oh, sorry, magenta.
magenta. Oh, so I see what you mean. I guess to try to highlight
It's a
the one.
iodide. I plus and I minus.
Okay,
There are two.
so they're not adding, are they adding the IO3 as a complex, or is the I coming from the perovskite?
The iodine is coming from the perovskite. They're just saying whenever the structure is exposed to oxygen, this is the reaction they'll see. And iodide is the most stable form. Always forget all the other names. Like they got IO2, IO3. So yeah, they just said that this is the more stable one out of the three
Okay.
different types of complexes.
So in figure C, what is the x-axis? Is it Fermi energy or what is that? E?
I think it's the energy Fermi level.
So what is the graph is saying that actually?
So when there's a V, that's trying to say the vacancy of lead
Mm-hmm.
is increased. Where if it's the I, lower or subscript I, it's
okay.
the concentration.
Is it number of vacancy or number of vacancy of this one or?
Or just the energy, because I mean the y-axis and the x-axis are stated energies, so
So then how
yeah,
do
they change the Fermi energy.
yeah, how do they compute different Fermi energies?
that's a good question. Guess I gotta look into that a little bit more.
I think it changes as the concentration of the I2
Vacancy?
gas they put in. So the more I2 they put in.
No, gas constitution is the constant, is the 10 to the power negative 4 bar.
Oh, never mind.
And it has a vertical line that's dashed.
No, that's optimal one. Maybe they're saying something.
Yes, 0.63 EV.
energies for the defect are dependent on the Fermi energy.
Is it something like they're changing the number of vacancy and then calculate the Fermi energy or something like that?
Probably.
Or could it be with the chemical potential? So when they vary the chemical potential, does that also vary the Fermi energy? And the one that's shown, is that the ideal Fermi energy?
Idea.
Would that make sense?
I don't know. The idea
So
of
like
Fermi energy.
here,
Yeah.
they have like point B.
Mhm.
So maybe that is the dashed line.
Okay.
And then as they go towards point A or towards point C, they see the other stuff. I don't know, I have no idea.
It appears that the dashed line intersects where the eye changes direction.
Yes.
So maybe it's just referring to where that bends. I don't know.
Yeah,
Yeah, I gotta read more carefully. Gotta think about it a lot more. Just
What is the difference of red line and magenta line? Is it PB something or
red line and what?
one's vacancy, one's
one is vacancy, one is extra land or something like that?
The concentration. It's
So the red line is
well,
defected one, magenta,
mhm.
is it?
Yes, the red one is defective line.
Yeah.
So Just for the purpose of the next talk, I'll just mention about non-adiabatic coupling. This is just the theory that nuclear motion has an effect on electronic states. So in adiabatic approximations, usually this effect is ignored, but in the non-adiabatic case, the perturbations that these have on the electronic states can lead to varying degrees of special overlap between the states over time. So this is also stating that the probability of an electron or a hole going from one state to another can vary in time. So this is usually done by solving for constant orbitals or energy levels, taking the motion of nuclei with respect to time, and taking into consideration the movement of electron.
What exactly is that equation at the bottom?
The equation to solve on the fly non-adiabatic coupling, or with pretty much nuclear motion.
Where it is, it kind of makes it look like it has to do with probability.
Probably due to the constant orbitals that are solved with respect to time.
Okay.
So what happens if you remove the ddt? What is it now?
If I remove the dd,
I think that will answer his
wouldn't that
question.
just be the adiabatic expression? No.
It's one of two numbers, and only one of two numbers.
One of two numbers.
And-
0,
And
1,
why?
because it's always 0 and 1. Nah, due to the fact,
What is 0 means, what is 1 means? There we go.
what is 0, what does 1 mean? So 1 is a normalized constant, right? Well, I mean, normalized a wave function is always equal to 1, ain't it?
Are they orthonormal?
Orthogonal. Yes, when it's equal to 1, it's orthogonal.
So then if I and j are equal, and you don't do the time derivative, it is equal to what?
One.
And then all other states are, if I and j are not equal, it's 0. But with the time derivative, you have non-zero probability of going from state I to j.
So it's a 0 chance. Okay. Oh, thank you for that. So, what they did right here too, they just took another methylammonium iodide structure.
Yeah?
Yeah.
Is there a connection between previous slide and this slide?
Yes, that, I was gonna get to that. So the NAC stands for non-adiabatic coupling. I guess I've heard to a lot of people probably have heard about non-adiabatic coupling. So that's why I just included them.
Because they don't have any idea about non-adiabatic coupling.
Yeah.
What is that? What is
What is it?
whether there are other questions?
Well, I was just going to ask, then what was the purpose of the previous slide from the previous slide?
Yeah.
That was also kind of...
Yeah, I was probably just a little awkward to throw that in there. I just thought that I just wanted to include it, but I could probably find a more simpler.
There is a
Logic.
clear reason. You just do not verbalize it.
I don't verbalize it. I just do it. I just say it.
And if someone has a question, you can put this as backup slide, and then you can be like, oh, this is how we compute non-adiabatic coupling.
So just use it as a supplement information instead of main slide?
No, not the mathematics.
Remember
just
your
what
second
is
year
yours?
seminar.
Yeah.
Yeah, no one paid attention.
Because there's all the equations that's
Therefore, you put audience at sleep and
Yes.
let your talk to go successfully. So, Daniel, let me try to answer the question myself. Connection between previous slide that attracted so much attention, then equation, and then this one.
Yeah.
So you are trying. I know we are over time. You are trying to explain influence of defects and dopants onto optical properties. In the slide that attracted attention, you just showed the connection between structural features and electronic properties. Very basic, like formation of energy and opening, closing the gap. But the optical properties of photoluminescence is often related to dynamics. What happens to your sample upon photoexcitation? There are several competing dynamical pathways, like emitting photon or emitting phonon, and competing between them. So one needs to go into dynamics of electronic state, which cannot be made without non-adiabatic coupling, which is the core basics to open the door into the world of dynamics. So it's connection of these two. After you introduce your non-adiabatic coupling, you can declare that you are skipping a lot of technical details, but after this door is open, you show example how some people in the community utilize non-adiabatic coupling and compute some dynamical properties. It looks like here you show dynamics.
Yeah. Sure.
But the connection was missed.
Okay.
And even if in this highly professional audience we miss connection, what to say about more general?
They probably, like Levi's talk, probably fell asleep after I showed the first equation.
But you may try to.
Try to keep audience awake. Yes. That is a challenge. So, anyways, for my last two slides, we have two models right here. They just took, it's the same structure, but on the top structure where it's considered figure 8, it's a lead-rich structure. All they did was take this tetragonal shape and cut it in half and expose the lead-rich, or the lead actually, that's hidden inside the cage, compared to the methyl ammonium that's exposed on the top part of the structure. So one of the key differences that you can see from the PDOS of both figures is the band gap in the lead surface is significantly smaller than the methyl ammonium iodide by almost half an eV volt. So what we found out here is the tau data or population is the same, well, relatively the same. The only thing that changes significantly is the non-adiabatic coupling that is found in the methyl ammonium iodide to be 10 magnitudes larger than the lead iodide. So also they took excited state populations between the both systems, and the lead-rich surface has found out to combine or delay much slower, so than the methyl ammonium iodide by almost 8 times much larger. So long carrier or long recombination dynamics is a great thing because the longer it takes to relax, the more potential you have to separate said charge that is found, while methyl ammonium iodide resurface just tends to relax quickly, much faster. So the reason to the high non-adiabatic coupling is they said usually was found out within this range of 2200 to 2500 to find the largest range of well, the highest disconfiguration of the shape, where they found out the methyl ammonium iodide, where it was sitting in its natural position, was rotating over time. So when you see those little structures, those little circles just means where it was relatively to where the non-adiabatic was at an all-time low, and it jump starts up to the higher part where we reach more of a relaxation at the 2500 range, where it's starting to go almost back to where it wanted, but it's just a rotation within the sublattice of the tetragonal shape. So that is found out to be the reason of it. Something that's not as clear too, when we look at the bonds that were made to the lead, you find out that you can see them almost go more flat. So that's sort of how you as the audience can indicate that the lattice is changing, or the cage. Is there any questions on this? Because this is the last slide. Yes.
So, what does this have to do with light emitting diodes?
Great question.
So, when we go back, we look at the excited state population, the lead-rich iodide surface takes much longer to relax. So that slower relaxation, you kind of have a chance.
Slow non-radiative relaxation.
Non-radiative relaxation. So when it comes to a slower non-radiative relaxation, there is more energy that is lost throughout the process of it relaxing. So it's less energy when it comes out to
Are you satisfied or not yet?
I know he ain't satisfied. I know he ain't.
So let me translate. If you replace the word energy to probability or chance for longer time, everything will be replaced. So if the non-radiative process is extremely long, it means the lifetime of the excited state is long enough, and during the time before non-radiative recombination happens, there is a higher chance for radiative recombination to happen. And radiative recombination is actually light emitting. So you're satisfied now?
Yes.
So I just translated what Daniel probably was thinking and trying to explain. Right?
Yes, sure.
So I had a
Yeah.
quick question. You said that the non-adiabatic coupling terms were 10 times, 10 magnitudes
Yeah.
larger.
Or it probably was 10 times instead of magnitude.
Yeah, so 10 magnitudes would be 10 to 10.
Oh, 10 to 10, so that'd be like 1,000 or.
No, that would be like 10 billion.
Sorry, yeah, I gotta choose better words. I think magnitude just sounds nice.
You suggest to, how long does your talk takes?
Less than half an hour from my side.
Well, I'm leaving at 5 because we have another event.
Okay.
For half an hour?
Yeah.
Okay, let's thank Daniel. And Daniel, please collect feedback to your presentation. So, next talk is Literature Club presentation by Jared on the Janus particles.
Okay, I'm going to talk on also on the similar topics here, solar cell applications. So this is a one paper. They synthesize Janus type nanocluster, heterocluster, and they calculate the multi-excitant generation, all other things. So So what is the importance of the multi-excitant generation? That's one of the reasons that I put it on the name, exceeding the Shapley Quasar limit. If you don't know about this limit, this is a theoretical calculation of possible maximum yield from the photovoltaic cell by using the sunlight spectrum. The maximum limit is theoretical calculation is about 33%. So we want to exceed that limit. So let's start with a very well-known image. That's this one. So I'm not going to talk everything. So if you just look on the very overall overview of this one, they have a lot of different types of photovoltaic cell, but everything efficiency is below 30% or 31%, and they have a multi-junction solar cell. Those are efficiency is more than 30, but it still is 50 or less than 50% overall efficiency. So if we want to go beyond that level, we need to do something, design something which is a new methods to create this current. So this is known as the multi-excitant generation process or KDM multiplication process. So in bulk material, this one, if you excite an electron at the higher energy, so usually what happens is thermalized to the front orbital, and then we can separate the charge hot and hole and electrons. But if instead of thermalizations, if there are some materials, by conserving their momentums and energy, the ground state electron can absorb the energy in excited to the excited state. So by absorbing one photon in that process, by absorbing one
sorry,
photon.
I lost the point. You said you separate electron and hole through what? How you
after
are separated? Like,
No.
I kind of cannot understand how you use this scheme to explain the separation of electron and
No,
hole.
I'm not separate. I'm just saying how was the KDM multiplication. I'm just saying the other one only. Okay, I mean, let's restate this one. So in those type of material, just absorbing one photon electron excited to the higher energy is create a hot electrons. And instead of thermalizations, these electrons, by the impact ionization, so it can release the energy, and another ground state electrons can absorb the energy and go to the excited state. So the main fact is you are, by absorbing one photon, now you got two pair of electron holes. So because of that, the overall efficiency of the photovoltaic cell can exceed the 100% efficiency. So this is a bulk material scenario. In nanomaterials, due to the quantum confinement, so we can momentum conservation is not that important in that case. So it's showing that image excited to the high energy is come here, and then another electrons is absorb the energy and go into the excited state. So this is the overall definition of kind of this process, multi-excitant generation process. So if you look on the literature, so there are.
I have a question on the first slide.
Yeah.
How momentum is related to this left?
In the bulk materials, yeah, when it's relaxing, we need to conserve momentum as well as the energy too in the bulk material, so to create this another hot electrons. Otherwise, it will just thermalize and energies go through the phonon or other related
A is
So
bulk, B
This
is
one is a
quantum
bulk.
dot.
Yeah, this one is a quantum dot.
What was that?
So is momentum conserved here, or?
Momentum conservation. If this figure, if you look at this total momentum change is here, and this is the electron momentum change. So if this energy want to absorb by these electrons, it need to be this much momentum.
So you mean change of momentum should be same?
Should be same for electron and hole. So that's momentum conservation. So this is just a few conditions. Although this everything is actually interrelated, so all then I just put it on the different bullets. So if we want to increase this process in any materials, we need to do first one just need to reduce the cooling rate, and then if you reduce the cooling rate, it will increase the probability of our impact ionizations. And then
So when you say widening the gap, you mean the band gap?
Sorry?
What kind of gap between electronic
okay.
states?
So this one is to reducing the cooling rate, so we can increase the widen the band gap. We know that in the bulk material, all state are very dense, almost considered as a continuous. So due to that, hot electrons can relux through the by dissipating the energy through the phonon, because they have a very small and different energy, so they have a more probability to couple with the different phonon modes. But in the nanomaterials,
So I would probably change the gap to the maybe splitting between electronic levels or something like this, right? Because again, what we usually call the gap, it's in the front area between the
actually,
edges.
I just basically mentioned the electronic states. That's okay.
Well,
Subgap offset.
Subgap.
then it should
okay.
be sub gap.
Okay, yeah. So this is not the band gap actually. So I mean the intrastate gap.
Or interstate.
Intrastate
Intraband
gap.
or something like
Intraband
this.
gap, yeah.
Sub gaps. This is usually people say sub gaps.
Okay, I'm sorry about that. Notice that.
So I had a question. So like on your LUMO, you have big old wide gap between like I guess the frontier LUMO and then the second one, and then the third one is.
It's a schematic figure. It's not anything major. It's just I'm showing. It's just. I'm just trying to show you there are some sub gap, widen gap compared to this kind of band gap.
Okay.
Or this bulk metal. They are more almost continuous.
Any requirements to the band gap of the materials for the increase in mag?
For increasing.
Does the gap make any role in it?
Yeah, obviously.
So you also want to increase it or decrease it or what?
It's not about the mag, it's about actually if you are utilizing the whole solar spectrum, because if you want to get the mag, we need to excite at minimum like 2 band gap, theoretically, more than twice as a band gap. So then you will utilize that excess energy to excite another electrons. So if your band gap is small, so you can excite higher energy, so that will increase the probability of creating the more MEG. So minimize the band gap also.
So you want to minimize the actual band gap,
Band
right?
gap,
But you
yeah.
want to make your sub gaps in the
Split, I mean.
valence and conduction bands, right? Large.
Larger. So that's why I told you everything is kind of interrelated, all of these things. And next, another one is impact ionizations. So if we want to have more impact ionizations, then we need to increase the Coulomb interactions. And if hot hole and electrons has a more strong Coulomb interaction, so that it increases the probability of getting the reverse of the process. So relaxation of momentum conservation, although this is not very important in case of nanomaterials, so because and also reduce the
What does
direct.
it mean, relaxation of momentum conservation? How you can relax the,
Relaxation
the
means
conservation law?
no, I mean
Momentum conservation, you can say it's a law for momentum conservation, and what you're doing is
relaxation means
relaxation.
in this case in the bulk materials, it's important. We need to match the energy as well as we need to match the momentum change. But in the nanomaterials, only energy is a fact. Momentum, we don't need to match the momentum.
So you probably want to say that you want to avoid the momentum conservation.
Yeah, it's the relaxation in that selection, not the relaxation. Relaxation means.
So
yeah.
again, I would choose a different word here.
Okay, I took this
Avoid the
actually this
momentum
word from this
conservation.
paper. Yes.
Oh,
so
I
that's
don't know.
why.
Limit, reduce momentum. How say reduce doesn't. Yeah. So you want really to avoid the conservation of momentum means to find systems where you don't need to conserve the momentum, right?
Yeah.
Okay.
So because in bulk material, if you want MEG, you need to match the both properties. So if you can skip one conditions, it increases the probability of happening this process.
And again, in the bulk, you can see the carrier multiplication, but you usually need to excite to
Very high
really
energy.
much high energy, like 5 band gaps or 6
Yeah.
band gaps, to make it efficient,
Yeah, I show that.
to
in
kind
the
of
top,
compensate for this relaxation
Everything
through the phonons.
And this is threshold energy, as you said. This is the threshold energy means the minimum energy to excite the materials to get the MEG. Yeah.
I have another question. So we know for periodic solids we need momentum, right? But you mean for
for nanomaterials,
Second
like
generation
which is
with-
a higher confinement effect, those kind of things.
So, suppose for nanowire, we
Mhm.
need momentum, right? But for quantum dot, probably not. You mean for multiple excision generation, we don't care momentum for any kind of?
It's not right, exact what actually we don't care. Is saying that is a more, flexible compared to the bulk solid in nano, because in the nanowire they have a momentum if you go to the one directions, and the overall momentum change is very small compared to the bulk. So yeah, so that's why it's important maybe, but it's increasing the probability because of your band become less momentum difference with the different K points. So, and this threshold energy.
But then back to your question, in a nanowires you have one dimension which has to be periodically extended, right?
Externally, yeah.
So you are reducing actually the requirements for the momentum conservation. Now you conserve momentum only in this direction. The other two, you don't need to worry about it, right? So again, you go to nanostructures, doesn't matter, you go from 3D to 2D, 1D, and 0D as quantum dots, right? So you reduce the kind of momentum conservation degrees of freedom, in other words. And going to 0D, you really don't need to it's not really taken into account anymore.
Yeah, so momentum conservation is a conditions, but now we are looking on the probability of happening or avoiding these conditions in what type of metrics, that kind of things. Yeah. So threshold energy is a minimum excitation energy to get the MEG. Suppose like as she mentioned in bulk materials, lead solenoid bulk materials, you need to excite minimum 5 times of the band gap to get the MEG process carrier multiplications. So it's very huge energy in this case. In the nanomaterials, it's reduced to in the 2.6 to 2.2 energy band gaps. So let's have some example like materials. For example, like first of all, these non-lead materials like CNT and 2D metal frames. They have a lot of citations. I did not put citations on. So most famous materials for the for multi-excellent generations are lead chalcogenide materials, usually lead sulfide, lead solenoid, and lead solenoids. And those are mostly studied materials for these applications and this process. And as you mentioned, the 1D versus 0D.
And again, what's the reason? Why is it the most studied? Oh, the most applicable in this case, right? What's the reason?
For because lead materials is a very small band gap. First of all, is about in the bulk is like about 0.3. So it's very easy to excite a very high energy, like 5 times. 5 times means like about 1.6 electron volt, a little bit than one. So that gives you the this kind of MEG process. Another one is about
what is a 2D graphene? Should it be graphene?
No, it's graphene.
Graphene sheet. 2D, nano frame.
But it's metallic.
No, graphene, not graphene sheet.
Yeah, it's metallic. The band gap is not open for graphene.
Yeah, there was some citation taken from this one.
Maybe it's plate, maybe it's quantum dots. So it's 0D rather than.
Yeah, this one is a plate. 2D means
in graphene,
graphene.
The gap is closed. It's a semi-man.
Is it functionalized?
Well, might be functionalized.
Yeah. I didn't read the whole paper, just to give for as an example, it is reported for multi-excellent generation process.
But you also have to do metal films.
Yeah, there are
which is also again, you usually 2-dimensional doesn't open the gap in the metals as well.
There have some Janus type materials. Janus type means 2 different metal plates, experimentally shown, and then also
then it's more complicated than just this thing.
Molybdenum something.
Oh, this is different thing. Then it's not metal films. Like
No,
they
no, I
use
just
more
meant
than
a
S
very
or more
generic
than
form of
something, then it's not metals again. Well,
Okay.
be careful because if you put just metallic structures,
Mm.
you're not expecting to have any carrier multiplication from it. There's no gap there.
Mm-hmm. So, but lead is open gap, so maybe let's all know it. So, and 0D versus 1D is mainly first is reported on the quantum dots. So the threshold energy is reported 2.623 band gap times the band gap to get the multi. But when it's creating the nanorods, threshold energy was similar, but band gap is lower. So then you can excite at low energy to get the energy more. And then most popular, mostly now new, relatively new is reported for the core shell structure. Core shell to get the this MEG process. Core shell structure because is a specific interesting property because excited electrons and hole are localized in the two different one, hole and shell. Sorry, core and shell. So you can separate that one. Another thing is the small core with a big and large shell, so they have a strong Coulombic potential between the electron and hole, so it will increase the probability of this process happening. But some problem about this type of a structure because hole is localized on the core and the electron is localized on the shell area, so it's very hard to separate the hole extract the hole from the core because core is surrounded by the shell. So although this have showing this multi-acceleration generation process, but it's very hard to make a device from these one things because with the time it will be saturated with hole and the device will efficiency become low. So because of that, we need to go to the different architecture of the materials or different new types of materials. Then people come up with this structure, the Janus heterostructure. So the shape of this structure is like one side is one type of materials and then one is another type of materials. So they started with the like cadmium selenide sulfide materials, and then by cation exchange, they are able to synthesize this architecture. One side is lead sulfide and another one is cadmium sulfide. So this is some experimental result is showing that this is the absorption spectra and before the starting the cation exchange reactions. They are showing the absorption spectra which is resemble of pure cadmium sulfide. And after sitting here in the lead solution, and then it started to growing the lead part, and it's giving it a longer tail for the low energy part. And this absorption feature is coming from the.
So it's absorption or emission?
This one absorption spectra. This tail part is coming from the cell and lead part, and this part is from the selenium. This for some
do they emit, by the way? Are there any data? Do they still emit?
They have emission result too. Yeah, they did some photoluminescence spectrum too. So to decompose the absorption spectrum,
because again, if we want to separate the charge, and let's say you excite, so your electron is one side, hole is on the other side, right? They spatially separated, then they have not a good chance to return back and emit light from. Right? So that's why I'm asking, like, are they still emitting? Because two things contradict each other. If you have well separated charge, then the emission should be actually reduced.
Yeah, but there is some portion of excited electron waste is give you the photoluminescence. So it's not actually bright emitter, I guess. They use this experiment.
So they need, but not really as good as just, let's say, cat selenide quantum dot lead selenide.
It's emit in the visible range and IR range, and they do that emission photoluminescence
spectrum. Have a dual emission.
Yeah, for this study. So if you decompose the absorption spectra, first this one black line, this is the pure cadmium sulfide quantum dots. So it's giving you this one bright peak, this coming from this range, and this larger is because of travesty. There is another one, and this is the Janus structure of the absorption spectrum. This overall solid line, this is indicating the overall absorption spectrum. And this low energy part, this bright peak, and the green line, they decompose in three different regions. This green line is after the excitation of the two electron volt energy. These two electron volt is lower than cadmium sulfide band gap and higher than lead sulfide. So you can assume that it's electron exciting only these regions. So we are getting the excitation from these specifically lead sulfide portions. So this portion is overlap with overall one. And there's another one, very long tail one. This one is getting absorption in this region, band gap region one. And the red one,
no, the band gap should be around 1.
Blue.
I forget that one actually, which one is which one. I need to look on the figure one. So blue line, yeah, if you look at the blue line is this line is giving us some trap state in interfacial state. So electron excited from interfacial state, excited to the interfacial state, and it's also denoted as a trap state. So this giving us this one here. And this very low energy, very high energy one, the very low intensity, this giving the excitation from this region, the cadmium sulfide region. So this is giving you the insight between the band structure of this quantum dot system, and from this one they extrapolate this symmetric band diagram here. So in the next part, they calculate the MEG efficiency, yield. So I'm going to
by the way, you need to go with your citations, right?
Yeah, I didn't put the because this one is
this
one is the same paper here in the previous paper here.
This paper.
Yeah. This paper here. This. That's why I didn't put the citation here.
Same paper?
This one is the same paper.
Okay.
Not this image. This image is taken from another paper, but these all.
But you're talking about the 60th nano 2018.
So in here, they plotted this with some result from literature as well as their calculations. So they considered, like, they took information from literature, 3 different kind of structure, nanodot, quantum dot, core shell one.
It's all experimental data.
All experimental
calculations.
Solid are their calculations, and the empty circle, those are taken from literature.
Calculations?
So, not calculations, literature data. Measurements. Sorry, yeah. And they synthesized the 3 different quantum Janus structure. One is 50-50, 50% lead sulfide, cadmium sulfide, and 60-50, 60 is lead sulfide and 40% cadmium sulfide. Another one is another 90% lead sulfide. But 90% lead sulfide is very close to the lead sulfide quantum dots, so they didn't able to calculate everything. So, and they're all blue lines are for mainly the 50-50 one. So initially, up to excited energy, this is the ratio between the photon energy by and times divided by the band gap of the materials. So it started the efficiency more than 1 after when this energy going to below about like more than 2, and then there's some plateau up to 2 to 3, and then excited very huge increase in after the 3 times band gap. So this line is a more close to the result from the core shell one. This is a green line. Green one is a core shell structure. It's taken from the literature. Is more close to the result of their one. So they're saying that the Janus structure is similar efficiency like core shell structure, but it will solve the other problem for making the device. And then how they calculate the quantum means, and then from the result, and they also trying to characterize their compounds, and then I'm going to show on this one. So they calculate the quantum will be using these equations. If this one is when you excite at less than 1 band gap, that means you won't get any MEG. And then if you excite it up to 2 band gaps, so you need to extrapolate up to 2 times and then 3 band gap, and then if
So
you
what is
excite
K?
it,
What is K?
yeah, K is a rate for rate of producing the one more exciton from the I exciton. Rate of the creating one extra exciton from certain number of excitons. That's they define as a rate of MEG, multi-exciton generation.
So it's a rate of B exciton formation.
B, not
So
specifically, I mean one extra exciton formations.
What is P?
Yeah, I'm talking about the P on the one, yeah. So if you look at this is the two process, actually one the rate of multi-exciton generations and the rate of cooling process. So overall yield is just a kind of competition between the two different process, or cooling rate and multi-exciton generation process. So this, and then they have another paper that derive this relation from the cooling rate and multi-exciton generations rate with the excitation energy by applying the Fermi-Golden rules, and then these ratio, the competition between these two can be characterized by another constant, so like this a P here. So from the P, you can characterize how efficient is your metal it is. So if you plot these equations from this here, and this line is plotted for very different compounds. This line P equal to 0.03 is compared to the bulk material. So that means you are getting started the MEG after exciting like 5 to 6 band gap times energy. So if you want to get the multi-exciton, you need to excite a very high energy one. And this one, that's selenium quantum dots. So you are getting the multi-exciton after exciting like 2.6 times band gap one. And so if you increase the P very, very large, close to the 10,000, so you will get this step line. This step line may indicating that is a 100% efficiency of getting the multi-exciton generations. So that means if you excited 2 times band gap, you will get 102 times multi-exciton generation. So naturally it's not possible here. And this line, this color is like, I should say, dark purple color. This is their line. This previous line you show the previous color. So by fitting with this line, they get the they consider that it's not possible, as I said, it's not possible to get the 100% efficiency. That means if you want to get 100% MEG from the exciting 2 band gap, so you need to excite from the 1 band gap higher to the frontal orbital of the hole, or 1 band gap below the frontal orbital, below the hole, HOMO. Then you will get the, you can extract the excess energy to get the another one, but it's not possible to get the exact symmetry in that case. So that's why they assume that the 20% of the photon excited in electrons, which is have enough excess energy to create another exciton, and 70% is exciting, but it's not meet the other conditions to create the excitons. And then putting this information in these equations, okay, this all the definition is how to define this band gap, this exciting excess energy. So you can consider the 3 different scenarios. Suppose like 20% of photons exciting electrons from here to here, and this energy is enough large to create the another excitons. So you are getting this energy efficiency from these 25% photons. And another one, symmetric case, suppose like this one, in this case symmetric, if you excite from here, you are losing this energy because this energy is not enough large to create the another exciton. And so now question is what type of state it is and why how much you're getting the exciton from this region. So they assume that these bands are some exciting from here, and these bands are close to that in the interfacial state. They have overlapping between sorry, not this band. This is the interfacial state. So interfacial state is they have a trap state, and these electrons, so this hot hole is going to the trap state immediately. As a result, this one is slow down the relaxation process. So this is getting the enough time to get the impact ionizations and giving us this one. But if it's exciting from the close to band edge here, they have no trap state coupled with this interfacial state. So this hole is relaxed faster, so it won't create your multi-exciton dimensions. So it's giving an example here, 3 different scenarios. Is going the interfacial state and giving you this one, and this is the creating another exciton here.
We have a question.
Mm-hmm.
So you said that if P equals 1000, then quantum
10,000, yeah.
10,000, then quantum yield is 100.
Yeah, there's a theoretical solution. You will get a 100%.
Yeah, that means those terms, except one, the other term should be 0 then.
Other term means
The series expansion?
this one,
No, top equation,
this part,
top one.
Oh, here.
Yeah.
So if you are getting the quantum yield equal to 1, if it is a P equal to 2 large, well, there are another. There's a P relation between the K, this one, and also you can change the excitation energy. So this is the constant here. If you have a fixed here number here, this is too big. So if you want to, that means this one is too big. That means this number is going to be large.
No.
Oh, sorry. This one is going to be too small. So too small means that time relaxation time is longer. Rate is very small. Relaxation time is longer because if you make it too large. So it's kind of, if you increase 1, so it's make another term is very small.
Okay, so maybe the rate of MEG, if it is higher, then the rate of cooling is lower, right?
Yeah. So if it is smaller, then it will increase the impact ionization probability. Ultimately, you will get a more MEG. So that's the kind of limiting case. So it's not possible in the real system. So that's why he's saying. So there, if you look on their line is close to that line. So that's indicating that they're more, very efficient. But all photon is not creating the exciton which give you the MEG. So they assume that 25% of photons, 99% give you the excitons. And then they extrapolate this result and then plot it in there. So then to prove their hypothesis, they calculate some, they did some computational calculations. Although they're saying that their computational calculation result is not 100% agreement with their experimental because they consider the very small quantum dots. So in the first phase, if you look at the dots here, very front orbital band, this band is coming from here. These are localized on the, and color is very confusing because this color and this color actually lead and chlorine. Bigger atom is chlorine, smaller one is lead. They put the same color. So it's localized on the other side, but in the very dense band. So this one is here. It's localized on the both sides. They have quantum cadmium and selenium part.
Can you, what paper you are citing? I missed it.
That's the same paper actually. Which one?
Have here.
So the number 1 or number 2?
Yeah, number 2.
So Gali.
Yeah, that was Julia Gali too.
And I don't see the year. This year's.
This year's is 2000.
Oh, this year, right? 2018.
No, this one is 2018 or 17.
I thought it just got published in September.
there were two around the one that you see this.
Okay.
This one is later one from last year, or this one?
Okay. So return back to you.
Okay.
Next slide.
There are also other ones. So that's getting the orbital energy. So this one is the delocalized over both part in the front orbital. So this is coming from the left side, is localized on the left side only. But they assume that it's not showing that very strong as left side localization is because of the small cluster. I don't know if they calculate bigger one, they assume that it should give a very strong localized on here. And this is not their good agreement with their assumptions. They also justify the same thing. This is the smaller cluster. If you get the bigger one, it will move inside the venue, but not too much. Their energy offset is very small. The unoccupied orbital of lead and cadmium part. And the C is showing the front orbital from the cadmium, and this one is for lead front orbital from the lead side one. So this is localized on the other part. And then in the next part, they're trying to prove their hypothesis by looking on the relaxation dynamics for fluids for photoluminescence relaxations. In the first one, this is the quantum cadmium sulfide nanocluster, quantum dots, and these are lead sulfide quantum dots. The relaxation time here is like 120 nanoseconds, and these are 2.2 microseconds. And when they give the visible range relaxation photoluminescence relaxation time for Janus structure, this one is they excited from the 2.8 and 2.1 band gap. This is above the cadmium and below the cadmium band gap. They found this relaxation time is much slower compared to the cadmium one. So that's why they're saying that wherever you range you're exciting, is not relaxing from the cadmium's side. But it matched with pretty close with the silver lead sulfide, but this is a 2.2 microsecond, this is on 1.7 microseconds, and this on IR emissions part. So they're saying from this part, they're saying that it's because of relaxing the lead part and lead sulfide part, and also this one is relaxing from the Travis state side, but this one relaxing from the frontier orbital of the quantum on the lead sulfide Janus part. So that's why it's infrared range, but this one in the visible range because the higher energy is relaxing from the Travis state. So
they do those in solution?
Yes, maybe, I guess. But although I didn't read their actually experimental methodology completely.
I don't know, it's just like if they have like such a... Wait, are those both at microseconds? Lifetimes?
Both means like, this one cadmium sulfide is nanosecond range.
But that's not the same, like, they're just showing that the quantum dot relaxes much faster.
Much faster, yeah. I mean, those are microsecond range. I mean, Janus structure relaxation rate is microsecond range.
Right, but I guess it's like if you use your cat selenide part has a shorter lifetime than lead sulfide, like you'd think that like if you had some sort of charge on the cat sulfide, like you could do some sort of energy transfer with the other one.
So this bottom part, these two are taken from the Janus structure. They are comparing with the pure cadmium sulfide quantum dots and lead sulfide quantum dots.
Right, but if you have like in your Janus structures, it's like you have one half that's lead sulfide and one cat sulfide. If you have a bunch of those floating around together, it's like if they get close enough, they could possibly exchange.
Yeah, so they're saying they're trying to prove. Or if you excited at higher energy, even if you excited the cadmium selenides, that hole is trapped by the interfacial state and eventually is going to the lead sulfide part. So that's why that's making it slow. If it's relaxing from the cadmium part, that's supposed to be fast, same as lead sulfide quantum dots. So that's the same thing they are trying to prove, is that is transferring through the interface, trapped in the interfacial state initially, and then is going and relaxing here. So it's saying it's not a relaxing from the quantum cadmium cellular part. And another thing is there's, but they conclude that hole is trapped on that in the state. But if you remember the band diagram here, so electron is going to the lead part, but electron was trapped here. So ultimately, it's helped to separate the electron and hole. But in photoluminescence process, but I'm not sure how they explain these things here because of this one. So, and this band is, another focus is the offset for LUMO of lead part and cadmium part is very small compared to the unbalanced band. So all this mechanism happening on the balanced band one. I mean, related to the hole. So hole is helping to do this MEG multi-accelerated process rather than electrons. So although the band is like type 2 structure, but it's helped to separate the hole and electrons because of the special properties of this trapping here. So otherwise, in typical scenario, if you're excited in the high energy, electron will come here and hole will go there. So it's very hard to separate electron and hole from the type 2 materials. But despite of type 2, it's separate the electron and holes. So in the relaxation mechanism, so there this kind of their summary of their what they are saying is because that they and the calculations they also found that they have they have a dipole, a strong dipole like 35 dirac. So they are saying that this strong dipole helps to increase the Coulomb interactions in the materials, and also the density of multi-exciton generations increases with the increase in the Boolean electron field. If they have there were some other papers I cited here. This paper is talking about the transient dipole moments with the Coulomb fields. They explain everything here. So they're saying that it support that calculations too. And another thing is cadmium sulfide and lead sulfide form a new state near the 2G band gap. It's kind of Travis state. They have overlapping in this region. So that's why it's helped to minimize the threshold energy. If you excite it up about close to the 2.2 band gap times, it's sufficient to get the multi-exciton. So higher energy intrinsic lead sulfide holes are rapidly trapped. These are the main points there. Is hole is rapidly trapped on the interfacial steps. So it slows down the relaxation for hole and ultimately goes to the multi-exciton generations. So this is the conclusions from the limitations due to the selection rules. So because of trapping here and a special asymmetry of Janus structure giving the stronger Coulomb interactions in the one, which is similar as the 1D materials, and the slower relaxation due to the interactions with the manifold of interfacial state interfaces, the overlapping between the cadmium and seleniums, and then it's facilitated the excited hole to go to the interface trap state, and then ultimately doing that their main purpose of slowing their swan. So they have a something they want to do, and also we can do, like, since they did not talk about anything about the nature or geometry or architecture of the interfacial state. They have anything changed, and we need to know that and how it's forming the interfacial states and how can we control this one, and is there any other way, like doping on the interfacial side, or is create the more efficient traffic state, or any other methods to slow down the whole relaxations. Another thing is changing the energy offset to make it more energy efficiency, because we need to look on the area of the interfacial stage as well as the size is 50-50. How it changes if it's pancake, we can decrease, we can utilize more sunlight. So that's all about this one. Thank you much everyone, and if you have any questions.
Thank you, Javid. There's a chance to ask questions if you have more curiosity. Questions 1, questions 2, questions 3. Meeting is done. Yeah, I thank all speakers for coming. Have a nice weekend, and there will be writing club on. There will be an announcement of other.